I'm presenting this model of coevolution of camouflage. This is a existence proof of constructing camouflage this way. I don't make any claims that it's optimal or correct or anything like that. Okay. To be clear, this is I'm speaking specifically about visual predation, predators that find their prey by looking around them, and optical camouflage. There are many other kinds of camouflage. All right, and probably familiar with this concept, but the idea is that camouflage interferes with the perception of objects, perception or recognition, generally by blending in with the background. This can be done by matching the color, texture, frequencies, things like that, and particularly disrupting the boundary of an object, so it's not even clear, where the object is. Camouflage can help prevent detection in that way, and it can importantly delay detection so that by the predator realizes where the prey is, it can run away. All right, so this slide. Oh. Well, that's a problem. So this hasn't changed? Okay. So I'm on like my... Yeah, okay. All right. That's good. Thank you. Sorry. So there was text about those things that I was saying, but anyway. So this is my slide with lots of text, but I'll just point out some key properties of the model. Which time do I use? This is based on negative selection and primarily genetic drift. There's very little selection pressure, just that the members of the population that are doing exceptionally poorly are the ones that are taken out of the population. Kind of neutral selection. I'm working with two populations, coevolutionary algorithm, and the magnitude is that 400 prey and 40 predators. The run lengths are about 12,000 individual steps. And now this is a steady state algorithm, so that's roughly like 30 generations in a generational genetic algorithm. The prey camouflage is constructed by nested expressions in a library for generating textures. We'll talk a little bit more about that later. The evolution and crossover in that part of the population is done with genetic programming, whereas on the other side, the predator vision is essentially a convolutional neural net, which I pre-trained and then is fine-tuned during... What's happening? I see my career flashing before my eyes. Okay, so the predators are CNNs. Pre-train them on a task of finding a conspicuous object in a field, and then they are fine-tuned during each simulation run for the particular background images and evolved camouflage. The fitness for evolution is relative, and it's established by tournaments of size 3. Okay, so it's a quick nature show here. So this is a moth on some tree bark. This is a locust, kind of a grasshopper-like creature on some sand. This is a katydid, a green katydid with white spots on a green leaf with white spots. It's doing a good job there. This is a type of caterpillar called a barren. Yeah, right? And it's right in the right place. Good job. This is there's actually a snake here in the middle. This is a copperhead. A friend of mine took this picture. He did not step on the snake. He properly detected the camouflaged object. This is a extremely cryptic gecko. I imagine this is on Madagascar. That's where all the cool geckos hang out. But so its nose is up here, tail here. This is a leg. Yeah, and in the middle, it's kind of like nothing going on here. Just move along. There's a bird called a frogmouth, and there's a nice picture of an acacia tree and a giant giraffe. Okay, so now that Attenborough is done with that, I'll get back to my model. So this is meant to be kind of an inspirational image as a natural world image. So here's a bird called a tree creeper. Nervous much? No. A bird, and it's just about to eat its lunch, some kind of bug that it's found on this tree limb. But these are the 3 primary components of the simulation model. So this is kind of what you should keep in mind as I show you these much more abstract things. So the 2-dimensional model, there are photographs in the background, just natural world photographs. During COVID, I would take walks around my neighborhood and, pull my phone out of my pocket, and that was kind of the setup. So early in the simulation, you can see that these disc-shaped prey are very conspicuous. They don't have the right frequency properties. They're the wrong color. Just everything is all wrong. But a little while later, they are, and of course, they only have the signal of whether or not they're eaten. So they don't have any ability to, the evolution doesn't look at the environment that they're on. They just know whether they survive. So here it is, kind of taking some Hail Mary shots. How about this one? No. How about this one? Okay. So here they're getting a little better. This one is not so good. These have this has better texture property, frequency properties, but the colors are wrong. It's kind of too green. But in these last 2 images, you see it's getting better. And again, there are 3 prey in each of these little square images. So there's one here, and I think this is the other one. Okay. Kind of a diagram of the simulation model. So on either side are these populations, and a roughly factor of 10 size difference. And again, all these parameters are just the first one that worked. That's okay, write the paper. 3 prey are drawn from the prey population, particularly from an island, a deme in the prey population. As I mentioned, one of the parameters to each run is a set of photographs, kind of arbitrary photographs, but it works best if they are similar in content and size and frequency and stuff like that. So it randomly chooses one of those, say, half dozen photographs, does a random crop on it, and that's what you see in the background. Oh, by the way, this is not the natural world. These are beans. And then in this, I'll show you a better picture of these tournament images, but there are 3 prey, and there's also some crosshair symbols in there. So that's the output of the predator. But yeah, in broad terms, take 3 predators, 3 prey. They are brought together in a tournament. They fight it out, and then from that, a ranking is established, a relative fitness, and generally the worst performing member of each tournament is eliminated and replaced. I do these population tournaments of 3. So one is unfortunately deceased. The other 2 become parents and produce a new offspring, which replaces the dead guy. Okay. I have a ad hoc metric that lets me measure how well the camouflage is working. I don't put a lot of faith in it, but these are 2 identical runs or runs on the same environment, same set of photographs. And then here, it's 2 different runs, one of which was more difficult than the other. So the easy one ramps up faster and then kind of gets stuck there, at least according to this metric. And the other one shows the slow increase on the harder problem. So the details of how the texture synthesis works, again, this is the natural world. These are a lovely genus of beetles called calligrapher beetles. They are just overflowing with morphogenic creativity. So you can see a bunch of different species, and this is kind of the many forms. I'm forgetting the Darwin quote. Most beautiful, many forms, most beautiful, I think. All right, and here's the embarrassingly simple version that I'm actually using. So it's a C++ library of texture operators. So here you see some simple cases. Probably, yeah, okay. There is I keep pointing to things. I just noticed that it's there. Okay, so this is a simplified version of this library. There's actually about 50 operators in it, but here are 2 of them. So this is one that creates random spots with lots of parameterization, and is operating on 2 other textures, which are just uniform fields of color. So blue spots on a white field, and here is stripes grading of green and gray. And then if you're familiar with how genetic programming crossover works, we're essentially editing these trees of operators. So take the blue and white thing, and then replace the blue with the striped pattern. So now you have circles of stripes on a white background. Here's the other way of doing that recombination. And just to make clear that there's a lot of different options. This is a noise warp operation applied to both of these 2. Okay, so it's like this, but more knobs, more choices. And real quickly, this is a convolutional neural net, which is the basis of the predators. So over here, this is meant to be one of these tournament images, goes through this kind of series of convolution layers, and then blah, blah, blah. And out the other end comes 2 numbers, which are a location within the image. So the predator looks at a image and says, here on the image, that's my guess of where the prey probably is. I won't say much about this, but this is what I use for pre-training. It's a synthetic database and spots on background, random spots on random backgrounds. Okay. And then this is a close-up of one of those, but let me draw back for just a second. I want to say how the relative fitness, oh, geez. When I was practicing this in my room last night, I had plenty of time to finish. Okay, so here we see a tournament between 3 prey and 3 predators. In this case, the predator has predicted this position, this crosshair, and in fact, that is one of the prey. So the important thing for the simulation is that the predator has chosen a position inside the body. Yeah, thank you. The so that prey is eaten, and that predator gets a meal. But the other two, these two prey escaped unharmed, but that meant that the other predators did not get a meal. So this one is removed. This prey and this prey form a new offspring, which goes back in the population. And the predators they get hungry. They don't die until they've missed like 20 meals, something like that. Okay. So luckily the rest of this goes pretty quick. So these are results. So this is, again, the spirit here is what Craig did in his neighborhood while COVID was happening. So this is a rock retaining wall at one of my neighbor's house. I'm the guy going around the neighborhood taking pictures. And in each case, there are 3 of these discs. Okay. So various rocks and then prey evolved to be cryptic in those environments. So I'll just I'll go through these real quick since I'm already out of time. There's a URL at the end if you want to come back and look more carefully. This is an oak tree in our backyard. This is leaf litter from redwood trees, sequoias. Is a flower bed. We saw this before. Some gravel, other kinds of leaf litter, dried beans. This is bean soup mix. And trees shot up on a clear day, so there's sky in the background, and a shrub with bright yellow flowers they're called, on green foliage. Okay, so the slides are online. If you want to see them again, take a picture of this slide. I forgot to make QR codes. There's a profusely illustrated project blog, paper on archive, and my contact information. Thank you for your attention. I'll stop.